So here's the statement of the rank-nullity theorem in the context of linear transformations. It says the following. So let T from V1 to V2 be a linear transformation, a linear map. Then the theorem is a theorem about dimensions. And it says the following. The dimension of V1, of the space here, the domain space of the transformation, equals the dimension of the kernel of T, which is a subset, a subspace, in fact, of V1, plus the dimension of the image of T, which lives inside V2 as a subspace. Okay? Now let me remind you what we have seen so far. When, in the specific case that T is given as multiplication by a matrix, so if T of V equals A times V, then we've seen that this theorem is indeed valid. Okay? And it was a direct consequence of some observations as to what is the kernel of T in that case, and what is the image of T in that case, in terms of the null space and the rank of the matrix A, and then it followed directly from the corresponding theorem for the matrix A. Okay? But now T is a general linear transformation. We don't know yet that it is in any way related to a matrix, and we're not going to use it yet. Okay? We're only going to prove this theorem from scratch, from the ingredients and from the stuff that we already know about linear transformations. Okay? Now, let me give you the idea of the proof. The proof is not too complicated, but it is going to be a mouthful. It is going to take a board or two. Let me give you the idea, and then we'll spell it out. Okay? So the idea is the following. Remember that this is a theorem about dimensions. Okay? So the kernel is a subspace of V1. Okay? So we're going to take a basis for the kernel and complete it to form a basis of V1. We know that we can always complete bases of subspaces to a basis of the ambient space. Okay? And then we're going to send that basis using T to V2. Okay? So we're going to get a set of elements here. They're not necessarily going to be a basis. In fact, they're not going to be a basis because there are a lot of fellows there that T sends to 0, because we started out with the basis for the kernel, right? So all the guys that were originally a basis for the kernel, T is going to send them to 0. Okay? So all these guys we're going to throw out. And what we're going to be left with is, at least in terms of the number of elements, is what we need in order to prove this theorem. So we started with some element. Let's add some numbers here to make this easier. So let's call n the dimension of V1. K is going to be the dimension of the kernel. Let me just check that it is indeed, yeah. K is going to be the dimension of the kernel. So what we need to prove is that the dimension of the image is n minus k. Then we're done. Do you agree? So we take K, complete them to a basis for n, send them to V2. Okay, we get a set of n elements here. Throw out those K that were originally a basis for the kernel, because they get sent to 0. Okay, so we're left with n minus k elements here. And we know, by the way, that they span the image, because they were an image by T of a spanning set, right? So we know that they span the image. If we can show that they're linearly independent, we're done. And that's precisely going to be the idea of the proof. Okay? So if that was too quick, here comes the slower version with all the details. So let's do it. So here's the proof. But the idea was really just what I said. There's no additional tricks or heavy machinery there. It's really a basic idea. Okay, so denote by n the dimension of V1, and by k the dimension of the kernel of T. And we will prove that the dimension of the image of T is precisely n minus k, and that would complete the proof of the theorem. Do you agree? Good? So far, everybody? Okay. So let's do precisely what we declared. So we need to give them names. Let's call them V1, V2, dot, 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 up to Vk. These are little v's. Let this be a basis for the kernel. The kernel is a subspace, we know that. It's of the dimension k, so it has a basis comprised of k elements. Call them V1 to Vk. Okay? So this is a basis for the kernel. Complete it, and we know that this can be done. This is a theorem that we had and proved a while ago. Complete it to form a basis for the entire space, V1. And we're going to call that basis, well, it starts with V1, V2, all the way through Vk, and then we completed it. So the guys that completed it, we're going to call Vk plus 1 all the way up to Vn. We know that in total there should be n of them because V1 is a space of dimension n. Okay? We know that T of V1 was an element and a basis for the kernel. In particular, it itself is an element of the kernel. So when you do T to somebody in the kernel, you get 0. Right? That's the definition of being in the kernel. So T of V1 equals T of V2 equals T of Vk. All the first k guys get sent to 0. Right? Okay. Since, let's write it, since V1 through Vk belong to the kernel. Good? Okay. So now we're going to take T and operate on all these n elements. Okay. This was a basis for V1. In particular, it's a spanning set for V1. Therefore, also, T of V1, T of V2, dot, T of Vn, do T to all these guys, spans the image. This was another theorem that we had and proved. If you take a basis or a spanning set for the domain, do T on it, you get a spanning set for the image. Okay? But the first k of them, the first k are zeros. So they don't contribute anything to the span, we can throw them out. Okay? Therefore, if we just take T of Vk plus 1, T of Vk plus 2, all the way up to T of Vn, this also spans the image. Because everything we threw out was just a bunch of zeros. Do you agree? Not happy.
How about the 0 vector in the image?
Well, you're asking, do these span 0? Of course, take 0 times this, plus 0 times this, plus 0 times this, plus 0 times this. You don't need to have 0 in a spanning set in order to span 0. Okay? Okay. So do you agree that this is a spanning set for the image? And how many elements does it have? N minus k. So all that remains, and that was my declaration for when I tried to outline the idea of the proof, all that remains is to show that this set is linearly independent. That does not follow from the theorem that says if you take a spanning set and T it, you get a spanning set. Here, right? We took a spanning set, T'd it, and we get a spanning set, but it's not linearly independent. There are a bunch of zeros here. So question, when we throw the zeros, is this a linearly independent set? if it is, we're done. It's a spanning set, it's linearly independent, therefore it's a basis, it has n minus k elements, and we're done. Okay? So, in order to complete the proof, we need to show that this set linearly independent. That this set here is not just a spanning set, but it's also linearly independent and therefore a basis. Do you agree? Okay. So here we're going to resort to the properties of being a linear transformation. And we're in fact going to show that it's linearly independent by definition. Okay, so let's do that. So let's give it a name so it's easier to refer to. Let's call this set B for basis. To show that B is linearly independent and therefore a basis with n minus k elements, and therefore we're done. Okay, so let's do that. Okay, so if, what does it mean to be linearly independent? I need to take a linear combination of these guys, assume that it's 0, and show that necessarily all the coefficients are 0. That's what it means by definition to be linearly independent. So if alpha k plus 1 times v k plus 1 plus alpha k plus 2 v k plus 2 plus dot 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 alpha n v n equals 0, sorry, we need to put t's here, right? And I'm not going to be able to squish them in. Alpha k plus 1 times t of vk plus 1, right? That's the elements that I'm trying to show. Vk plus 2 up to alpha n t of vn, right? A linear combination of the elements of B. If it equals 0, then we have to prove that all the alphas are 0. That's what it means by definition to be linearly independent, right? So if we have such a combination, then by properties of being a linear map, a linear transformation, we know that we can throw in the alphas, right? So we can write this t of alpha k plus 1, vk plus 1, plus t of alpha k plus 2, vk plus 2, plus dot 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 t of alpha n vn. Right? A linear transformation absorbs the scalars. Furthermore, if we have t of a sum, it equals the sum of the t's. I'm again using the properties of being a linear transformation. And I mentioned before that passing from a linear combination, throwing the linear combination inside the t is a standard step in many, many proofs which use the fact that a transformation is linear. So t of alpha k plus 1, vk plus 1, plus alpha n vn equals 0. Do you agree? And in fact, going from here directly to here is, even that is a legitimate step in this, in where we are. Okay, we know that already, that t of a linear combination is the linear combination of the t's. That's the property of being linear. Okay, what does it mean that t of somebody, whatever this somebody is, equals 0?
Or it's 0 or it's inside the kernel?
It's not or, it's inside the kernel. This element is an element of the kernel. By definition, t of it is 0, right? So alpha k plus 1, vk plus 1, plus dot 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 alpha n vn belongs to the kernel. That's what it means to be an element of the kernel, right? But we already have a basis for the kernel, right? namely v1 to vk. So this thing here, this linear combination of the v's with index from k plus 1 to n, is an element of the kernel. Therefore, we can write it as a linear combination of v1 to vk. Do you agree? Mm-hmm. So therefore, this element, alpha k plus 1, vk plus 1, plus dot dot dot, alpha n vn, can be written in some way as a linear combination of v1 through vk. There are some alphas, some coefficients, which I'm going to call alpha 1 through alpha k, such that this equals alpha 1 v1 plus alpha k vk for some alphas. Do you agree? If it's an element of the kernel, and v1 through vk were a basis for the kernel, then it can be written as a linear combination of these elements. Okay? With some coefficients, I want to call them alphas. You can call them betas if you prefer. Doesn't matter. Okay? Everybody good? Okay. So now I have an equality here. I can move all these guys over here. Okay? So I'm going to get a linear combination of all the v's, which equals 0. Do you agree? So therefore, alpha 1 v1 plus dot 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 plus alpha n vn, that's the right-hand side, minus alpha k plus 1 vk plus 1, minus dot 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 minus alpha n vn equals 0. I took all of these and then subtracted all of these and got 0. Do you agree?
Yeah, just those should be alpha k, vk in the plus, I think.
Oh, here it's a k. You're absolutely right. Thanks. This is the first k ones. This is from the right-hand side. And then I subtracted the left-hand side and got 0. Do you agree? So I have a linear combination. Now everything is in V, in V1. Okay, everything is in the domain space. It's a linear combination, which equals 0, of the elements of the basis. When can you have a linear combination of the elements of a basis which equals 0?
Not the alphas are 0.
Only when all the alphas are 0. So all these alphas are 0. In particular, alpha 1 through alpha k are 0, but that I don't care about. But in particular, alpha k plus 1 through alpha n have to be 0, and that's what I wanted to prove. Okay? So therefore, all alphas, and in particular, alpha k plus 1 dot 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 alpha n are 0. So we started with a linear combination of the elements of B, t of vk plus 1 up to t of vn, and we assumed it equals to 0. We showed that necessarily all the coefficients are 0. That means that these guys are linearly independent, and therefore B is a basis. Okay? So one second. Therefore, B is linearly independent. We already knew it was a spanning set, and thus a basis for the image with n minus k vectors. So the dimension of the image is n minus k, and that completes the proof of the theorem. Yes, questions?
I didn't get the last part. How did you decide if all alphas
From here to here?
Yeah.
I have a linear combination of v1 through vn. It equals 0. v1 through vn was a basis for v1. If you have a linear combination that equals 0, all the alphas are 0. That's what it means to be linearly independent. We know that v1 through vn are linearly independent. They're a basis. By definition of linear independence. That's the definition. The definition of linear independence. No theorem, no nothing. If you have a linear combination that equals 0, all the coefficients are 0. Okay? That's the definition. Good? Okay. So this completes this proof. Okay? You may need to read it again. As I said, it spans 2 boards. Okay? But the ideas are very basic, and many of these ideas, when I do spend time and ink and board for a proof, it's not because I think that it's fun. Well, I do. But I think that it incorporates ideas which are important, not just for this particular proof, but in fact, ideas that show up in many other proofs and other exercises and other even questions that you may encounter in homework and in exams. Okay, so there are many ideas here that are very basic and very important regarding linear transformations. It's a very basic theorem. Okay? Okay, so back to what we know. We finally know this rank-nullity theorem in general, for a general linear transformation. Note that in everything we did here, we didn't say the word matrix. We didn't at all use the fact that we've already hinted to. That's going to be the next clip, okay? Showing that, in fact, any linear transformation can be represented by a matrix. But we didn't use that, okay? So this is completely valid in its own right, okay? One more thing that I want to say. Usually after we give a theorem, we would give many examples. But in fact, we've seen many examples. In every linear transformation that we have written as example for whatever so far, I always showed you, hey, pay attention to this. The dimension of the domain space equals the dimension of the kernel plus the dimension of the image. So we've seen it exhibited in all the examples we've seen so far. So I'm not going to give more examples right now. Okay, it's a fact that we've seen many times. Okay, what I do want to do is write 2 corollaries, 2 statements about linear transformations that follow from this. Okay, and the nice thing about this is that it really gets used a lot. It's a very useful theorem, but many times in statements that don't involve a priori. The statement itself doesn't involve the kernel and the image. Okay, they just get used as tools. So let's show these 2 corollaries that I want to show. Let me find them. Oh, here they are. So corollary number 1. If t from v1 to v2, a linear transformation, is 1-to-1 and onto, so if it's a 1-to-1 and onto map, then the dimension of v1 equals the dimension of v2. So a 1-to-1 and onto map between 2 linear spaces can only occur when they have the same dimension. Okay? This is a part of a more general statement that we also hinted to already. The notion of, I can even throw the word, the notion of isomorphism. When do we think of 2 spaces as being the same? Okay? And we're getting there. It's gonna come soon, but this is part of it. We can see that if we can move back and forth linearly, respecting the linear structure of the spaces, that's what a linear transformation which is 1-to-1 and onto means, then they share dimension. They are of the same size. Okay? That's not the full statement, but it's a partial statement. Okay? So let's prove this. I forgot to write is linear, and obviously it's linear because we're in a linear algebra course, but nevertheless it's worth mentioning. Then the dimensions are equal. So let's prove this. The proof is going to be very short because we're going to make use of the theorem. So I'm going to start the totally naive way. I'm going to start with the dimension of v1 and hope to get to the dimension of v2. So what is the dimension of v1 equal to? Well, n is just a name, but what is it equal to by the theorem? The dimension of the kernel plus the dimension of the image. Do you agree? That was the theorem. What's the dimension of the kernel? 0. Why? Right. We have a theorem, we know, that when a linear transformation is 1 to 1, that's if and only if the kernel is 0. And in particular has dimension 0. So this equals 0 because this is 1 to 1. So maybe we'll write here. This is 0 since t is 1 to 1. And what's the dimension of the image?
It's the dimension of V. Because it's
The dimension of which v?
V1.
V2. The image is a subset of V2, but since the map is onto, everything is in the image. V2 equals the image since t is onto. Do you agree? Okay. So the dimension of the kernel is 0 plus the dimension of the image, which is the dimension of V2, and we're done. So this is a direct consequence of that theorem, and try to prove it without it. Okay, you'll see that you run into a lot of, how do you start? Okay, do you agree? Everybody good? Okay, another corollary. Corollary number 2. And this corollary here may look a bit surprising. Why surprising? Because for general functions, it's absolutely false. Okay, but for linear transformations, it's true. So if the dimension of V1 equals the dimension of V2, so if we take a linear map between two spaces which share the same dimension, okay, and it's a linear map, it doesn't necessarily mean that the map is 1 to 1 and onto, of course. Right? You can take the 0 map, send everything to 0. That's a linear transformation. It's obviously not onto, and it's not 1 to 1. Do you agree? Okay? So just the statements that the converse of this is obviously false. Okay? If the dimensions are equal, it doesn't mean that the linear map has to be 1 to 1 and onto. Okay? That would be way too much. But then, if it is 1 to 1, then it's automatically onto. And if it is onto, it's automatically 1 to 1. So if you're taking a map between two dimensions, between two spaces which have the same dimension, then those properties of being 1 to 1 and onto collapse to being a single property. It's one if and only if the other. Then t from V1 to V2 linear is 1 to 1. Let's write it like this. If the dimension and t is linear, then t is 1 to 1 if and only if t is onto. Okay? And this is not in general true for functions. Okay? If you take a function, it can easily be 1 to 1 and not onto, or be onto and not 1 to 1. The properties are very different in nature, but for a linear map between two spaces of the same dimension, they coincide. Okay? So let's prove this. We have two things to prove. One, that if the map is onto, then it's necessarily 1 to 1. Two, that if the map is 1 to 1, it's necessarily onto. Okay? And it's going to follow from this. Okay? You can even, just by looking at it, you can see where it's going to stem from. If it's 1 to 1, then this is 0. So the dimension of V1 has to be equal to the dimension of the image, okay? And that's going to be equal to the dimension. That equals, by assumption, the dimension of V2. So the image is everything, and the map is onto, and vice versa. Okay, do you see that it's going to be a direct corollary? Let's write the details. I may need another board, so let's take another board.
Could you give me examples, one example of V1 and V2, which their dimensions are equal, but they're not one-to-one or on?
No. You're, okay, so
Or
you're looking for a linear map between two spaces which have the same dimension. A linear map. You can't say that V1 and V2 are one-to-one and onto. That doesn't compile. What's one-to-one and onto is the map. Okay? So if you're taking two spaces, V1 and V2, which have the same dimension, for example, 2 by 2 matrices and R4. For example, 2 by 2 matrices and polynomials of degree less than or equal to 3. Those are linear spaces, very different spaces, which have the same dimension. If you have a map, a linear map between one and the other, that's one-to-one, it's going to be also onto. I can't give you an example of one that's only one-to-one and not onto, because the theorem says, or the corollary says, there is no such example. If it's one-to-one, it's automatically onto. Okay? Okay, so we need to prove two directions. If it's one-to-one, then it's onto, and if it's onto, then it's one-to-one. So here's this direction. This direction was assume that t is 1-to-1. So if t is 1-to-1, then the kernel of t is 0, right? This we already know. Therefore, the dimension of the kernel of t is 0, because it's the 0 space. Therefore, by the rank-nullity theorem, the dimension of V1 equals the dimension of the kernel, 0, plus the dimension of the image. That's the rank-nullity theorem. But the dimension of the image well, we need to write it differently. We need to write here. This is what we know. So the dimension of V2 equals the dimension of this one. This is the assumption of the theorem, of the corollary, right? We're assuming that we're looking at two spaces that have the same dimension, and this equals, by the rank-nullity theorem, 0, the dimension of the kernel, plus the dimension of the image. So the dimension of the image equals the dimension of V2, and therefore, this is another statement that we had improved. If you have a subspace which has the dimension of the ambient space, then that subspace is everything. Remember that theorem? You can't have a 4-dimensional subspace in a 4-dimensional space which is not everything. Okay, we proved that. Therefore, the image is V2, and therefore, T is onto. Good? Okay, so it's very basic. It's like, fiddling around with some numbers, right? This is 0, this is everything. But there's theory hiding here, right? In particular, this theorem is not just an observation. It required work. Okay, the other direction. Now let's assume that t is onto. If t is onto, and it's basically going to be the same idea as just reading it backwards. So if t is onto, then the dimension of the image equals the dimension of V2, right? Because if t is onto, the image is V2. That's what it means. And therefore, they have the same dimension. And this equals the dimension of V1. That's the assumption of the theorem. By assumption. Right? So the dimension of the image is already the dimension of V1, But by the rank-nullity theorem, if we add here the dimension of the kernel, it should still be equal to the dimension of V1. So we don't have a lot of dimensions left for the kernel. Do you agree? Okay, so by the rank-nullity theorem, the dimension of the kernel has to be 0. There's nothing left for it. Okay? And therefore, the kernel is 0, which implies that t is 1 to 1. Good? So these two statements, these two corollaries, indeed follow directly from the rank-nullity theorem. Okay? And we're going to see why they're useful. We're building up to that statement, to the definition and the idea of isomorphism, of when are two spaces just two different ways of looking at the same space. Okay? Okay, questions so far? Again, this was a bit theoretic, but theoretic is part of this course. There's some theory here, and it's really just understanding the definitions and the notions we're dealing with. Okay, we didn't do anything. We didn't throw in any deep ideas. Okay, everything was very basic. Was really one little step after the other, just following very basic things, as long as you know the definitions. Okay, if the definition of what it means to be linearly independent suddenly slips your mind, then there's no way to do this. There's no way to understand it. Okay, you have to know the definitions. Okay, so let's stop here. In the next one, what we're finally going to do is prove that any linear transformation can be written in terms of a matrix. How do we do that? That's coming up next.